So I'm with this title because it's quite convoluted. Machine learning was already covered by Professor Szwamiński on the last talk, so thank you. And as for the very short-term forecasting, we need to underline this very in this, because in literature, often the short-term means they had to several hours forecast, so that we add this. And as for the continuous intraday power market, this may be something that you see for the first time, so let us discuss this too. Okay, so the main workhorse of the European Power Exchange in Germany is the head on the short term. So most of volume is traded there, and is traded in the auction scheme on 12 o'clock. And later we have the auction on 15 o'clock, which is the intraday auction, and we also trade there quarters and block products, etc. And later there is also the intraday continuous market, which we consider today. At the 16 o'clock, it starts and it trades up to 5 minutes before delivery. And why is that? Why do we need this whole machinery here? Basically, the market changed a lot in the recent years because we introduced a lot of renewable energy sources. And it can happen that, for example, wind just stopped blowing. And we do not have energy for our consumer, so we need to buy something. Or on the other case, the wind can start blowing again, and or the sun can start shining again. And yeah, we have too much energy, and we need to do something with it. For example, sell with negative price. Yeah, so those are the problems, and the solution is the continuous market and trading close to delivery. So our motivation to tackle those quite complicated structures is first filling the gap, because the continuous market is not really considered in the literature. Here are examples of two works, really, the Marciasz and Rafał Beron professor work on the beating the naive, for example, and the recent work of Professor Ziel and Hirsch, PhD student, I think, and they consider the probability forecasting of the trajectories on this market. But yeah, those are really two words that I can think about right now. So the second point is supplementing our previous research, because me and Dr. Jan Jantura, we worked on the optimizing of portfolio that consists of selling the energy on buying the energy on the intraday auction market and day-ahead auction market. So we forecasted the prices for the next day, our products before the 12 o'clock, and then we decided which part of energies to sell or to buy on the auction on 12 and on the auction on 15 o'clock. So the forecasting of continuous energy market will allow us to extend this strategy for the next day. That will be cool. So for me personally, the motivation is the interesting data. It's quite interesting and quite challenging. We have 96 products, so the quarter hours traded parallelly, and additionally, every trade, of course, corresponds to a unique volume, and is traded not in equal spaces, but whenever the bids were matched. Okay, so here we see the data in 3D. So for a weekday, for a Wednesday, and on the x-axis is the offer time, and on the y-axis is delivery quarter hour. And we clearly see the pattern that we saw on the Dr. Jan Jantura presentation. So we have the morning peak, we have the evening peak, and the peak hours are from 8 to 21, maybe to 20. And we have higher prices, and in the night we have even negative prices, but on average, because it's average over whole year, on average it's like very, very low price. Then the standard deviation is really low, like long for the delivery, and it's high only at the front of the market. And here we have the counter of trades, and the counter shows us that yeah, a lot of trades happen like 3 hours before the delivery, and it's not really out earlier. Okay, and something is happening during the weekend. To be honest, I do not yet uncover why is that, but it's clearly different than the weekday, and therefore we decide that we need to put some dummies, so some indicators of the day of the week if we want to forecast, because yeah, the model will sit that and just go crazy because that's really different from this picture. So yeah, that's why it dies in the model. Okay, and to put this into perspective more clearly, maybe I also show you the plot of territories of prices, and we see that they start really not during the 16, because here's the time before delivery, and this is the 16 o'clock on the previous day, and they start whenever the trade happens. So we do not really have the equal length even in time, not in trades. So that's problematic, and it's even clearer here maybe. So this is the counter of all trades from the 2020, and we can see that up to like 4 hours before the delivery, nothing happens sometimes. Yeah, the number of trades increases like here. This is delivery for 15 o'clock, so that's maybe like 5 hours before, and 4. Yeah, and later the volatility is, as I showed before, quite large. Even in the number of trades. Okay, and later, what is the processing of data to cope with those issues? So based on the already tested approach of Thiel and Kirsch, we decide that we assume that if nothing trades, the price should maybe stay the same to unify the length of our territories. So if nothing trades from the left, we extend the price from the left to the right until the next trade. And using this assumption, we process the data in such a way. So we first average the price to minutely granularity to have the minutely sequences. Then we repeat the last known price according to the assumption here, and then we match to the left. So we extend the last known price from the left to the left to match the 16 o'clock, and then we match to the right. So we extend the last known price to the right to match the full horizon. Sorry, we extend the average price from the 3 hours before now. So this is somehow corresponding to the ID3 index. There's an index on the market that is taking the 3 hours before and taking average volume weighted average from them. So we are doing something similar, but not before delivery, but before current time, to extend the territories and have the same length. Okay, so here are the preprocessed territories from the 3rd of November 2018, and those are the same territories that I showed before row, but now they're preprocessed and have the same length. And you can see that I put the same value where there is no trade. So here's the same value, and here is the trade, so it decreases and so on. Okay, and later, after we process the data and already have the equal lengths of territories, we applied some transformation. So first, we difference with the with lack of age, so horizon. Why is that? I tested the approach, the whole modeling and forecasting approach on the row transformed data, like those territories, without differencing it, and it performed really poor because stationarity is not found there. And so we approached it with differencing, because now we do not need to focus the whole territory, like the whole move of the price, but only the delta in every point. So we differentiate it with horizontal age, and then we aggregate the volume also, because we do not have a lot of days really in our sample. It's only 425 in the first window. So we we aggregated the volume, we summed it over territories, so that the assumption is we do not really want to know what was every volume of every transaction, but we want to know what was the total volume traded in every minute, because that's something that is really important. And lastly, we standardize. I do not write the formulas here because we standardize in several dimensions, because every model that we consider has dimension of input, but we use the mean and standard deviation to standardize the data. Okay, so now we can turn to our experiment, and we have the resulting from the processing and transformation data of the size. So it's days times number of variables times the length of territories of each variable, and it's 2 times age plus 20. 20 is the availability of data delay. So we must wait 20 minutes till the last info from the market arrives. So that's why it's h, so horizon plus 20 here. Okay, and first question, what do we want to trade in the experiment? We want to trade for 15 o'clock in this initial experiment. So it's 61/4 of the day. We trade at 14 o'clock and we use the expanding window to train our model. So we start with 425 days and expand it by days of 2020, on which we test the model using the mean absolute error. And we compare it to check if it's okay, because in forecasting, there's no such thing as just good forecast with no performance comparison. So we compare it with naive, and naive is taken just like the last known price from the market, and we assume that the delta will be 0, yeah, so that the price would stay the same. Okay, and now the models. To go through them, we have the Lasso model. So it consists of the prices for the deliveries close to our forecasted delivery. Prices are taken from the left and from the right, and we take the L0 and L1 for those prices. Then we take the dummies, but we take the linearized version of the dummies because Lasso performs better on them. So we take the 7 columns of 0 and 1s, indicating the number of the week, and then we take the aggregated volume as the last variable. Okay, and we estimate the shrinkage parameter using the cross-validation with 10 folds. And the next model is the multi-layer perceptron, MLP, just dense neural network. So that's really quite simple concept of calculating the output. Here we have the example of output of the layer L+1. So this is just activation function applied pointwise to the multiplication of weights through the input from layer L. We've added 1 at the beginning of this vector because we need to add the bias sample. So to estimate the weights, we use the gradient descent with layer grade C, and this is the loss function, which we take the derivative over weights. Okay, and here's an example of how it should look with 1 layer. Yeah, so that's really quite simple concept. And the second model, the second network that we use is LSTM. And here I do not show any equations for the propagation, but really what should we know is that our data, as you maybe remember, has the shape of days, time, number of variables, time, number of time steps, and it's ready to be put into the LSTM because LSTM uses the last time steps of variable to learn about the history of it. So yeah, so here's the cell state that is updated by the input in every step, and by the sigma layer that puts the number between 0 and 1 to decide what we forget and what we update here. And yeah, this is the output of the cell, and it is good in the sense that it allows us to use those information from the previous time steps more than our dense network. And lastly, we have the idea that excites me the most, maybe because it is quite new to me. It was actually introduced 5 years ago by the authors of this work, and it is neural tangent kernel. The idea is that we can expand our neural network in the series, and so that we linearize it here because that's linear. And here we can look at it just as applying the linear regression to the space transformed by the derivative, the gradient of fx w. So this is the network with inputs x and initial weights w0, and this is, as you maybe see, the kernel regression. So finding the kernel of this network allows us to solve the network using the kernel regression, and it is the same as solving the network if the network layers width is infinite. And here is the the equation for our kernel, it consists of the brilliance of text. So that's quite a neat idea, and it allows us to over-parameterize the model, so apply the infinite layers, and in assumption it will lead to near zero training error and better test error. So it is already implemented, at least partially, because there are implementations for dense, for residual networks, and for convolutional neural networks in the JAX using in the Python using JAX on the neural tangent GitHub. So yeah, it is ready to use, and the documentation is quite neat. And here are the results using those models. So as you can see on the left column, the model MA is always respectively worse than the naive. So taking just the last known price on the pricing of 120 minutes. But if you take the average of naive and our model, for part of the models we get the better results, significantly better results. And that's something that is very promising to us, especially for infinite residual neural network. Residual neural network means that we are skipping some connections and just putting the same input that was before them. Okay, so that's the result for 120 horizon, and now for the best models and the ones that are estimating in let's say feasible time, we checked what's the performance for several horizons, so from 30 to 420, and as you can see, the last so average over several sets of L0 and L1, so we shifted the window over which we took the traded products a little to get different forecasts so that we can average them. And also the same position was performed for dense and residual NTK. And after averaging them, the NTK showed better results. I did not check the significance of them, but for now they are visually better, and I think I can tackle them to be even better. So that's something promising. And the dense and residual NTK are being calculated even a little bit faster than lasso using the validation scheme. So to sum up, NTK approach is faster, as I mentioned, than lasso, and yields better results, and it's significantly better in the terms of speed than MLP and LSTM. Remember that we are forecasting in the very short time horizon, so that every minute counts, and we do not want to wait like several minutes until something finishes working. So in assumption, this should be instant solution, at least for the user, not something that we need to wait for. And then the combining forecasts with naive approach gives us significant results. It's like 4.5 or even 6% on the average. And then the future work consists of applying methods of finding the optimal weights of for averaging of the forecasts. And also, I would like to derive and implement the NTK for LSTM, because to my best knowledge, it does not exist right now. And it would be nice to see how the overparameterization of this model would maybe help us, because as we've seen, the LSTM performed good, and if the infinite dense network was good in the NTK, maybe the LSTM will perform good too. So that's the bibliography or something. Something broke here, sorry. I cannot switch the bibliography, but I will try this. Yeah, and thank you.